Right, so today we're going to be looking at the product rule for differentiation. So this is when we have a product of two functions, so two functions multiplying together. Now, if that was just a pair of brackets, so let's say we had, I don't know, x plus 3 times 3x squared minus 6x to the power of 5, we could treat that as a product rule, this thing being multiplied by this thing. But in that instance, we'd probably just expand out the brackets and not bother with the product rule. However, there'll be instances where we can't expand, and so therefore we need another strategy. So say, for example, if this had been x plus 3 times the square root of 3x squared minus 6x to the power of 5. Okay, it wouldn't be possible to expand that out. Or certainly not as, it would be more complicated than it's worth to somehow combine that together to avoid the product rule. And there'll also be situations where it's impossible to when we get to introducing our other functions. So, for example, if we have e to the x times sine of x, you just can't expand those out. And so now we need a rule for when we have a product of two things. So you'll recall in a previous video we talked about the fact that if you have a function which is the result of adding or subtracting together two functions, then its derivative is just the derivative of each of those two functions added together, okay, or subtracted. However, if it's multiplication or division, the same isn't true, okay? So if it is, if it is f of x times g of x, the derivative of that is not the derivative of f of x times the derivative of g of x. And same if we were dividing two functions, f of x divided by g of x is not the derivative of f divided by the derivative of g. We'll need something else called the quotient rule for differentiating a quotient of two functions. So today we're going to be looking at, okay, if it's not this, what is it? How do we differentiate when we have two functions being multiplied together? And once again, I'm going to go through the proof of that. This rule doesn't come out of nowhere, and actually you have enough algebra to understand this proof. Again, it's not about you, I'm not expecting you to be able to replicate the proof or make the proof yourself, but I want you to see that when we differentiate f of x times g of x, we get something that actually follows all of the rules of differentiation that we already know and understand, okay? So we're using differentiation by first principles, okay? So we know that when we differentiate by first principles, given that I've got this called f, I might call it something else. So let's say we're trying to do, I know h is also confusing, a, b, c, f, g, h, let's call it m, let's say, okay? Let's say we've got a function m of x. If we wanted to differentiate m of x using first principles, we know it's the limit as h approaches 0 of m of x plus h minus m of x all over h. Okay, so we want to have a look at doing that for this function, okay? So therefore, we need to be able to think of this function at x plus h, which is that, minus this function at x, which is that, all divided by h, and taking the limit of that as h approaches 0. Okay, so then let's manipulate this. Alright, so one of the things we need to do is sort of add and subtract in a term that's going to then enable us to do what we want. So I've chosen here to subtract f of x times g of x plus h, and then I'm also adding in f of x times g of x plus h. So this is actually equal to 0. So I haven't actually changed the value of this, but what this is going to allow me to do is to split this up into two halves that I can simplify, okay? So in this instance, we still haven't taken the limit, so that's still going to sit out the front there. I'm going to focus on sort of dividing this fraction into two, down the middle there. So I'm going to have f of x plus h times g of x plus h, take away f of x times g of x plus h, and I've got that over h. It's the first half of the fraction, and then I've got plus f of x times g of x plus h minus f of x times g of x, and then we've got all of that over h. Okay. Now, we can do a couple of things at this point. What I'm going to do two things at this next step, is I'm going to factor out the common factors. So there's a common factor of g of x plus h in this fraction. I'm going to factor that out. There's a common factor of f of x in this fraction. I'm going to factor that out. The other thing I'm going to do is I'm going to apply the limit to both fractions separately. So if I'm taking the limit as h approaches 0 of this fraction plus this fraction, it's the same as taking the limit as h approaches 0 of that fraction plus the limit as h approaches 0 of that fraction. Okay, so I'm going to do those two things at once in this next line. So we're going to have limit as h approaches 0 of, and I'm going to factor out that g of x plus h, and then left in the fraction we've got f of x plus h minus f of x over h. And then plus the limit as h approaches 0, and this time I'm factoring out f of x, and left in the fraction I have g of x plus h minus g of x all over h. Okay, so once again I'm going to split the limit up further. So if I'm taking the limit as h approaches 0 of all of this in here, it's the same as me taking the limit as h approaches 0 of that times the limit as h approaches 0 of that. Okay, so I'm just going to break that up, and then we'll think separately about each of those things. So we're going to have limit as h approaches 0 of g of x plus h multiplied by the limit as h approaches 0 of f of x plus h minus f of x all over h plus the limit as h approaches 0 of f of x, and then multiplied that by the limit as h approaches 0 of g of x plus h minus g of x all over h. Okay, so in breaking this expression down in this way, we've now got some interesting things happening. This here, that is the derivative of f. And this one here, that is the derivative of g. Okay, so let's have a look at what's happening. Let's take our limits. So the limit, the first term here, the limit as h approaches 0 of g of x plus h. Okay, so as h approaches 0, this essentially becomes 0, so it's just g of x. Multiplied by, we just talked about the fact that this is f dash x. That's what that is. Plus the limit as h approaches 0 of f of x. Now there's no h's in f of x, so as h approaches 0, nothing's changing with f of x. So it's just going to be f of x, and then times, and as I said, this bit here, this is the derivative of g. So times the derivative of g. And there's our product rule. I'm going to write it in a slightly different order in the box down here, but essentially, if y is f of x times g of x, then dy dx, the derivative of that, is derivative of f times g plus, leave f as it is, and multiply that by the derivative of g. I write that in a particular order in this instance. It wouldn't matter if we switched these two things around, it wouldn't matter if we switched these two terms around because it's addition. However, in order to be able to use the same sort of patterns when we look at the quotient rule tomorrow, it's sort of helpful to think about them in a certain way. So if you've got two functions multiplying together, you take the derivative of the first function, multiply that by the second function without changing it, plus you leave the first function as it is without changing it, and you multiply that by the derivative of the second function. So that's your product rule for differentiation. It's worth noting that the product rule is given on the formula sheet, but it's given in Leibniz notation. So it's given as, I think from memory, if y is u times v, then dy dx, is derivative of, it's not written that way either, it's written as du dx times v plus u times dv dx. Okay, same idea, derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. But just to be aware of the notation. So there's no reason for ever getting the product rule wrong. It is on the methods formula sheet, and the methods formula sheet is available to you in both exam 1 and in exam 2. So even if you don't have it in your notes, there's no reason for getting it wrong. Okay. The methods formula sheet, there's a copy of that on the inside cover of your blue booklet. It's a formula sheet you should be familiar with, particularly now as we're moving into differentiation. Quite a number of the rules that we use appear on that formula sheet, so worth being familiar with what's there. Okay, let's have a look at some examples using the product rule. So one of the challenges with using the product rule, which we'll talk about a little later on, is you actually recognising when you need to do that. And we're going to get a lot of practice with it as we gradually introduce each of our functions throughout the rest of this chapter. So it's really important that you get used to identifying, oh, I've got two functions multiplying together. Now, I want to be clear about that it's only if you've got two functions multiplying together. In fact, let's go back here for a second. So let's say you've got an equation that is y equals 5 times x squared, okay? So you could think about that as a product, 5 times x squared. And so you could use the product rule. So it's the derivative of 5, which is 0, multiplied by, I leave x squared as it is, plus, I leave 5 as it is, and I multiply by the derivative of x squared. And so this all just becomes 0, and I get 10x. So if it's a number times a function, you don't need the product rule, because you'll get this 0, half of it's irrelevant anyway. So you're just literally taking the derivative of the function part of it and multiplying that by 5. We've already been doing that, okay? So I find sometimes students overcomplicate things. For example, down the track, when they've got something like 5 times sine of x, they'll try and use the product rule. You absolutely don't need the product rule there. It's a number times a function. It would be, however, if you had x times sine of x, that's all of a sudden a function times a function, because the derivative of x isn't just 0. So you would need to use the product rule in that instance. So we'll talk more about identifying the product rule later in this section, but also as we move through the examples. The second thing is I wouldn't use the product rule unless I had to. I'm going to do it here. I'm going to do this example in two different ways to show you that it's completely unnecessary to use the product rule here, and in any opportunity that you have to simplify the expression or the function before you differentiate it should be taken, okay? If you were to use the product rule here, okay, let's try. So we've got dy dx is going to be, I differentiate the first function in my product, so that is 2x, and I multiply that by, I leave the second function in the product as it is, and then I add, I leave the first function as it is, and then I differentiate the second function, which in this case would be 3x squared. Okay, and then I've got a lot going on here, so there's a lot that could be tidied up. I'm going to expand out those brackets and collect together some like terms. So I've got 2x to the 4 plus 16x plus x squared times 3x squared, so that's 3x to the 4, and 2 times 3x squared, so that is 6x squared. And so I have 5x to the power of 4 plus 6x squared plus 16x. Okay, perfectly fine. However, if I had simply expanded the brackets beforehand, x squared times x cubed is x to the power of 5, plus x squared times 8 is 8x squared, plus 2 times x cubed plus 16, and differentiated that, 5x to the 4 plus 16x plus 6x squared, I get to the answer much more efficiently. So if you don't need to use the product rule, if you are in a position to be able to expand out the function so that the product rule is not going to be required at all, absolutely that would be the choice. Okay, so this would certainly be the better option, the more efficient option here. Okay, alright, so part B. Now again, in part B, it would theoretically be possible to expand out those brackets and not need the product rule. However, this is going to require quite a lot of expanding. So this is a situation where, okay, whilst I could expand it, I'm not gaining efficiency by doing that. Okay, so we're going to use the product rule in this instance. So we've got our two functions. There's our first function in red, and there's our second function being multiplied together. So we know that the product rule says that we differentiate the first function, so the red one, which is just going to be 2. And then we leave the second function as it is, so that's 5 minus 3x all to the power of 4. And then we add, and we leave the first function as it is. And then we find the derivative of the second function, so the green function. Now, the green, to differentiate that, the green is going to require the chain rule. Okay, so hopefully after the previous lesson, we're getting quite good at our chain rule. So remembering with the chain rule, I don't want you to need to let u equal 5 minus 3x and all that. Let's just imagine covering up the 5 minus 3x. Let me get my black highlighter again. Okay, let's just imagine actually, maybe if I make it dark grey, we'll be able to not have to erase it again. Let's just imagine that we can't see that 5 minus 3x. So we're covering that up. We've got something to the power of 4. We differentiate that. Something to the power of 4 is 4 times that something to the power of 3. And then using chain rule, we multiply by the derivative of that inside that we've just covered up, so the bit covered in grey, and the derivative of that is negative 3. Okay, so then when we have expressions like this, we quite often end up with, I'm just going to tidy it up slightly, so the second term there I've got negative 12 as the number outside of all that, 2x plus 1, and 5 minus 3x all to the 3. Now that's perfectly fine. If the question says differentiate this, no problem. However, maybe it's a multiple choice and it says which of the following is equal to this, and so it doesn't actually match this version and we need to manipulate this further. Perhaps it says differentiate this, expressing your answer in this particular form, in which case we might need to be able to manipulate this further. So while I'm going to manipulate this further, if the question just says differentiate, you've done that at that point and I would stop. Okay. However, what we want to look for is common factors, and I mean common factors between the red and the green sections. Okay, so I'm noticing that there is 2 in common, 2 and 12, 2 is a common factor there, but also 5 minus 3x is common. Now there's 4 of them in the first term, but there's only 3 in the second term. So 5 minus 3x cubed is common to both the red and the green sections. Okay, so then if we focus on what's left when we've taken that out. So if we've divided the red section by 2 times 5 minus 3x all cubed, we've still got 5 minus 3x left there. Okay, minus, and then if we've divided the green section by 2 times 5 minus 3x all cubed, 12's been divided by 2, so we've got 6. We've still got that 2x plus 1, but we've divided away all of the 5 minus 3x all cubed. And now left in this big bracket at the end, we can expand and collect like terms and tidy that up. So we've got 2 times 5 minus 3x cubed, and then in here we've got 5 minus 3x minus 12x minus 6. So we've got 2 times 5 minus 3x all cubed, and then we've got negative 3x minus 12x, so minus 15x and minus 1. Now, there's a couple of different things that could happen here also. That common factor of negative 1 in that second bracket, we might choose to take that out. 5 minus 3x all cubed, so it becomes 15x plus 1 in there. The negative's out the front here instead. The other thing that could happen is because when we're cubing a negative, it's still negative, we could choose to put that negative back in to that bracket and instead write this as positive 3x minus 5 all cubed, 15x plus 1. So those 3 things there, they're all the same, okay? But just, again, being aware of that the fact that they're the same and how you can manipulate between the two. Similarly, if the question was just differentiate, you'd stop here, okay? But if you needed to get it into a particular form, it needed to be fully factorized, you might need to solve it, so therefore factorizing it's helpful. It is worth being aware of how to manipulate it to that particular point. Okay, let's have a look at C. So again, we've got a product of 2 functions. We can't just expand all of that out. I'm just going to start by writing the square root as a power. So this is x plus 1 to the power of a half. And then let's focus on our product. So again, we've got a product of 2 things. We've got this quadratic times this square root. Okay. So product rule says we differentiate the first part of the product, that is the bit highlighted in red, and when we do that we'll get 2x, and then we leave the second part of the product as it is, and then we add and we leave the first part of the product as it is, and we differentiate the second part of the product. And again, in this instance, differentiating that section highlighted in green is going to require the chain rule, because we've got a composite function, x plus 1 inside of x to the power of half. So we're going to have half x plus 1 to the negative half, and then multiplying by the derivative of the inside, which gives us 1. So again, I did that. Cover up your inside, you've got something to the power of a half, derivative of something to the power of a half is half times that something to the power of negative a half, and then we multiply by the inside. Okay. Alright, sorry. Okay, so now let's focus on tidying this up a little bit. So my original expression had square roots in it. I'm going to choose to write my expression back with square roots, and also because I can tidy this up. So again, the first thing I would say is you could just leave your answer as 2x times x plus 1 to the half. This will be plus 1/2 times x squared minus 3 times x plus 1 to the negative half. If the question is just differentiate this, at this point here you've done that. Okay, there's no reason to do anything more than that. However, you might be asked to write it in a particular form, so let's work through the algebra of how this might be able to be written in different ways. So this is 2x times the square root of x plus 1, and this is x squared minus 3 over 2 times the square root of x plus 1. If I then want to combine those terms together, I'm going to need a common denominator. So this is already over 1. So if I multiply the top and the bottom here by 2 lots of root x plus 1, so I'm going to get, we'll have 4, that's multiplying by 2. And then when you do root x plus 1 times root x plus 1, sorry I left the x out there. When you do root x plus 1 times root x plus 1, that just becomes x plus 1. Okay. So all I've done there is create the common denominator by multiplying the numerator and the denominator in the first fraction. We've multiplied by 2 lots of square root of x plus 1, and we've done the same to the denominator. Okay. So now we've got a common denominator, we can combine them together. Let's expand out the numerator of the first fraction as well. So we've got 4x squared plus 4x, adding that with the second fraction, x squared minus 3, and we've got all of that over 2 times square root of x plus 1. And so collecting like terms on the numerator, we get 5x squared plus 4x minus 3, all over 2 root x plus 1. So again, you've answered the question at this point if the question is to differentiate, but if you're going to want to do something with it, I don't know, substitute into it, solve it equal to something, if the question specifies that it should be written in a particular form or whatever it might be, then you do need to be aware of how to do that algebraic manipulation. So I'd like you to try and get into the habit of practicing that a little bit. Okay, now part D. Now again, part D we could treat as a product rule. We could think about this as being x squared plus 1 to the half times 1 minus x squared to the half, and do, think about derivative of the first part multiplied by the second part plus leave the first part as it is, multiplied by derivative of the second half. However, we should again, if we can simplify before we differentiate, we absolutely want to do that. So if we think about, we know that when we have the square root of AB, it's the same as the square root of A times the square root of B, which means this works in reverse. If you're multiplying 2 square roots together, this is just the square root of x squared plus 1 minus x squared. Now if I write this as this, 1 plus x squared, 1 minus x squared, that's a difference of 2 squares. So that is 1 squared minus x squared squared. So it is the square root of 1 minus x to the 4, and in fact we don't need to think about it as a product at all. It's 1 minus x to the power of 4, all to the power of a half, and we can just use the chain rule. So you'll notice here I haven't changed anything here. This is all equal to y. We haven't differentiated at all. At this point, we're now going to differentiate, and so it has to be equal to dy dx. Again, covering up your inside function, you've got something to the power of a half, and so you're going to get half times that something to the power of negative a half, and then you're going to multiply by the derivative of the inside, which is negative 4x cubed. Alright, tidying up a little bit, the half and the negative 4 will become negative 2, so we've got negative 2x cubed, 1 minus x to the 4 to the negative half, and we could choose to write that back with the square root, negative 2x cubed over square root of 1 minus x to the 4. Okay, so again, don't use the product rule if you don't have to. Simplify as much as you can first. If you still need the product rule, then you need to use the product rule. If not, then great, you don't. Okay, example 2 here. Find f dash at 3, so the derivative of f when x equals 3, if f of x equals x cubed plus x times g of x. g of 3 is equal to 5 and g dash of 3 is equal to 2. Okay, let's focus on what you're trying to find here. Sometimes people get themselves really bogged down in all the information. That's what we're trying to find. So if we want to find the derivative of f when x equals 3, the first thing we need to focus on is finding the derivative of f. Okay, so f of x, in this case, is x cubed plus x times g of x, which means that f dash of x will be 3x squared plus, and now here we've got a product, x times g of x. Two functions, linear function, multiplying by an unknown function. So we need the product rule. So derivative of the first function is 1, leave the second function as it is, plus, leave the first function as it is, multiply by the derivative of the second function. Okay, so f dash x is 3x squared plus g of x plus x times g dash x. Alright, now we want f dash at 3. So that means 3 times 3 squared plus g of 3 plus 3 times g dash at 3. And this is where the information here is useful. Okay, so we know that g of 3 is 5 and g dash of 3 is 2. Okay. Alright, so we can put that information in. So we've got 3 times 3 squared, that's 27, plus g of 3 is 5, plus 3 times g dash at 3, which is 2. So we've got, that's 32 plus 6, and so 38. Okay, finally over the page, as I said, the challenge becomes, it's fine in this exercise where you're doing an exercise on the product rule, so you're probably going to need to use the product rule. But questions realistically aren't going to say that, it's just going to say differentiate this. We might be differentiating it for a whole other purpose. You might have to decide to differentiate. And so it's about being able to identify when you need the product rule. So when you have one function times another function. So in the functions below, we want to identify whether we need the product rule, which would be if we've got our function is f of x times g of x, whether we need the chain rule, which remember is for composite functions, so f of g of x, whether we need both, so we had a combination of product and chain rule required in an earlier example, or whether we're going to need neither. Okay, so let's have a think about these different functions. So you've got y equals sine of x squared plus 3. So this is a composite function. This is a quadratic function, x squared plus 3, substituted into a sine function. Okay, so composite function requires the chain rule to differentiate. The second box, so I'm moving across the table to the right, y equals x squared plus 3 multiplied by sine of x. That's multiplication in there. Okay, so this one you've got a quadratic function multiplied by a sine function. So that's a product of two functions, and therefore we'll need the product rule to differentiate. Okay, the third one, top right box, we've got e to the power of x squared plus 5x. So again, that's a composite function. You've substituted the quadratic function, x squared plus 5x, into the exponential function, e to the power of x. So composite functions require chain rule. Okay, part E, we've got 2x e to the x. So again, you've got a linear function, 2x, being multiplied by an exponential function. So that is going to require product. Now we'll have a look at in subsequent videos how to differentiate e to the x, how to differentiate sine x. I'm not asking you to differentiate these, I'm asking you to think about whether you would need the product rule to differentiate. Okay, the next box along, we've got 1 over log e of x. Okay, so I want to think about this actually as being log e of x to the power of -1. And so we can think about that as a chain rule, log e of x, all that to the power of -1. And so we would, it's a composite function, log e of x substituted into 1 on x. Similarly for the next question, same idea. 1 on x is going to require the chain rule because it's actually 5 minus 3x to the power of 4 all to the power of -1, and we would use the chain rule. -1 times this thing to the power of -2 and then multiply by the derivative of the inside. So we definitely need chain rule there. It's a quartic function inside of 1 on x, substituted into 1 on x. Okay, the next one here, we've got x cubed times, okay, so there's a product in there, so we've got these two things multiplying together, this cubic multiplied by this degree 20 polynomial. So we're definitely going to need the product rule, but the second part here, this bit, is also going to need the chain when we have to differentiate that as part of the product rule. So as I said, we did an example like this earlier where we had both product and within the product rule we had to use the chain rule. So this one is going to require us to use both our product and chain rules in conjunction. Okay, cos squared x. So let's just review what this notation means. Remember when we write cos squared x, it actually means cos of x all squared. And so therefore we can see that as a composite function. You've got cos of x substituted into x squared. Okay, so it's a chain rule because it's a composite function. Alright, again the next one's also going to be a composite function. You've got the tan function substituted into the square root. We would probably write that as tan of x to the power of a half before we differentiated, but regardless we're going to need to use the chain rule. Tan substituted into the square root. Okay, next one, x squared times log e of 5x. Okay, so this is multiplication here. So we've got a quadratic function multiplied by a log function, and so we're going to need product rule. Log e of x cubed. Again, you've substituted x cubed, a cubic, into a log function. It's a composite function. That's going to require the chain rule. Sin x plus 3 times cos x. Okay, so the plus doesn't require any special rule. We just differentiate the sin x and differentiate the 3 cos x. The 3, it's 3 times cos x, but 3 is a number, not a function, so we don't need the product rule here. We actually don't need either chain or product rule here. Once we know how to differentiate sin, we'll just do that. Plus 3 times whatever the derivative for cos is when we get to those. Next one, 5 times sin of x. Again, it's 5 times sin of x, but it's not a product of two functions. If it's a number times a function, you don't need the product rule. The derivative of 5 times sin of x is just 5 times the derivative of sin of x. So we don't need either chain or product rules here. Y equals x times sin of x. Okay, so x is a linear function multiplying by sin of x. Its derivative isn't 0, and so we are going to need the product rule here. That's a big one where I see commonly students don't recognise product rule required there. X times sin of x, two functions, the simplest possible linear function multiplying by a sine function. You're going to need to use the product rule. And the last one here we've got root x, so x to the half times log e of x. Again, a product of two things, and so we're going to need the product of two functions, I should say. It's not just about two things. We're going to need the product rule to differentiate that one. Okay, so as I said, we'll get a lot of differentiation practice as we gradually build up through the chapter, and actually the most difficult part is not just how to execute the product rule, but to accurately identify that you need to use it in the first place. Okay, so the work today is again on a worksheet. It's printed in Appendix B of your blue booklet. So best of luck, off you go and do that.